Hello, everyone. I don't think most of you know who I am. I don't think I've interacted with most of you. So my name is Professor Israelowitz. I like to be a little casual in a course like this, so you can just call me Josh. Um, and yeah, I will be taking over for this course. So to alleviate any fears of how this course is going to be run, uh, we're just going to talk about math. There's not going to be any, history, politics, ethnicity, whatever discussions. I'll occasionally do a little bit of math history, but anyway, this is a math course. We'll stick to math. Okay, and so what I want to do is really start from almost start from scratch and really just go over what the goal of what normally would be the first half of the course. I think we're already halfway into the course. I mean, halfway into the semester. But right, so the initial goal is as follows. So what I want to do is basically develop a notion of length. Okay. And in particular, what I ideally want to do is develop a notion of length, a really good, nice notion of length for all subsets of the real line. More generally, it would be nice to develop a notion of area for all subsets of R2, or develop a notion of volume for all subsets of Rn for an integer n. In this course, we'll stick with the real line, just like the book does. And I will use Follin's real analysis book very closely. I personally think it's an excellent book. I actually was the one who convinced Professor Bacciano to use it in the first place, just because I think it's really perfect for this level of course. Okay, so right. So let me be a little more precise. So more precisely, what do we want? We want a function that takes in a subset of the real line. So here script p is for the power set. So we want a function that takes in a subset of the real line, spits out something between 0 and infinity. Certainly, we do want infinity to be possible. For example, the length of an infinite interval is obviously infinity. I don't think there would be any controversy in saying that. So we do want to include infinity. Okay. And there's just some obvious things we want to be true for a good notion of length. And here m, I should say, very generically represents measure. We're kind of measuring the length of a subset of the real line. Okay, so right. So first of all, fairly obviously, the empty set should have 0 length. It's empty. It has no length. Okay. B, if I'm given an interval, I don't care if it's closed, open, half closed, half open, finite, infinite, whatever, any halfway decent, way to measure the size of a set better give me the length of an interval when applied to an interval. So in the future, I'll denote this by L of I. script little l for length. Okay. So right, again, any halfway decent, useful measure of size of subsets of the real line better coincide with the length of an interval when applied to an interval. And C, if we can write a subset of the real line E as the disjoint union of other subsets, this kind of bracket union, I don't know if any other courses used it, but when I write kind of this rectangular U here, that means disjoint subset. We're going to use disjoint, we're going to take countable disjoint unions so often, it's just useful to have a brand new notation. So yeah, so if we have the disjoint union of sets, countable disjoint union of subsets of the real line En, then intuitively the size or the length of E should just be the sum of the size or the lengths of En. I mean, just drawing a picture here. Let's say this is the real line, and let's say for example, E. Draw one more. Let's say this is E1, E2, E3, and et cetera, et cetera. These could be shrinking. Who knows what they're doing? I'll put this down below here. Now, we'll admit one thing with my video lectures. I do talk very slow. I think it's better to talk slow than it is to talk fast. And on YouTube, you can go up to double the speed. So, if I'm talking overly slow, I'm not offended if I find out that people are watching my videos at double speed. Honestly, when I review my own videos, I watch it at double speed. Because again, I just personally have a preference that it's better to be a little, it's better to talk a little more slowly than it is to talk a little too fast. Right, so here E is going to be the union of all the E's. And so intuitively, right, the size of E is, the sum of the red lengths intuitively. All right, right. So one kind of obvious consequence of this, and actually of A, would be that this also applies for finite disjoint unions. In particular, if E is a subset of the real line and E can be written as the following disjoint union of the finite disjoint union of these subsets of the real line En, well, let's define En for n bigger than big N to be the empty set. So again, just to emphasize, we're not given this, we're defining this. Okay, then certainly E is going to be this countable disjoint union. Basically, it's just all these ENs plus tacking on the empty set. Well, the empty set's empty, so it just doesn't really, you're not adding on anything to this finite union. Okay, well, what does that mean? That means if we have C true, then the size, for now on, let me just call it measure. The measure of E would be this infinite sum Okay, well, because of A, obviously, when n is bigger than n, we just get 0. So we're just adding 0 infinitely many times. That's still 0 by definition of an infinite sum. So this is going to be equal to, try to fit it in here. Never a good idea to try and fit something into a digital whiteboard corner, or probably blackboard, whiteboard in person. So this is, yeah, like I said, basically it's this sum here plus adding 0 to itself infinitely many times, which is just 0. So in other words, yeah, as I said, this property C here, thanks to 1, is true for finite unions. If E is this finite disjoint union, then the measure of E is going to be this finite sum. And I should mention that I will draw pictures every now and then in this course, because I feel that like pictures do help give you intuition. They don't prove anything. I want to emphasize that. They don't prove anything at all, but they really do kind of help you. Okay, right. So, and last but not least, the last property we want is that if I have a subset of the real line and little x is any element of the real line, it's any real number, and if I translate e by x, in other words, I basically move e, then I better get the same set. I mean, that makes intuitive sense. You take a subset and you move it, you've just moved it. You haven't changed its size, right? Or rather, this should be a property of any reasonable measure of size or length or whatever. Okay. And again, if there's, I mean, I'm sure we've all seen this notation here. This is just the set of all E plus X, where E isn't big E. Okay. So there's a problem here, and we'll talk more about this later. But this is just impossible. You can't do this. You literally cannot find a function that takes in the subsets of the real numbers, spits out something between 0 and infinity, where all of these are true for every subset of the real line. You gotta sacrifice something, and you can prove. We're going to talk about this a little bit more. We're not going to exactly prove it, but you can prove rigorously that you can have actually. You just simply cannot do all this. You cannot have this function m where all 4 of these properties a, b, c, and d are true for all subsets of the real line. But that's not a big deal. And in particular, there's a very practical solution to the situation we're in. And that's as follows. And this is going to motivate what Professor Bachanu started a little bit. We're going to find a very special collection of subsets of the real line. And this is going to be, this is often called the collection of measurable sets. More precisely, we'll call this in a future the collection of Lebesgue measurable sets. So the point here is that this very nice collection is going to contain every single practical subset Great. Yeah, so this collection here is going to contain every single practical subset of the real line that you will ever possibly encounter in really your future studies, in your future graduate studies and your future research studies if you end up doing mathematical research. Okay. Um, and we'll find a measure function, a length function, not defined on the whole power set, but on this collection script M, where A through D is true when restricted to this collection of subsets, this collection of measurable subsets. And we call it measurable because the idea is that we're going to develop this measure length function, and this length function is very well behaved. It's behaved in a way that we would want it to be behaved on this nice collection of measurable sets. These are sets where we can define a good notion of length. And I really do want to emphasize, and this is absolutely amazing, as in my opinion, that this set script M will literally contain any practical possible subset of the real line that you could ever imagine yourself ever dealing with. And we'll be a lot more precise as we go forward in the course, just what I mean by that. Yeah, so I want to talk about some applications and why we even bother with this. You might think, well, is it really worth it to develop, to spend all this time just to develop a useful notion of length for subsets of the real line? And that's debatable. So there's many more, but two very useful applications of what we're going to do in at least the first half of the course. I should say, to be honest, the second half of the course is already up on YouTube. I don't know if I'll even get to any of it because we are already, be honest, in the second half of the course. Right, so two applications are, first of all, the probability theory. So I don't want to say much about this because I have actually two lecture videos on applications of everything in this course to probability theory, and I even do talk about some interesting stuff. Particularly, I prove there the Kolmogorov 0-1 law. Maybe I forget what else I do there, but yeah, the bottom line is all the tools and all the techniques we develop, basically doing just what is here. In other words, kind of answering this, developing this practical solution. These are the same tools and the same techniques that are needed to develop carefully probability theory. Okay. So if you're interested in probability theory, you have to intimately understand everything we're going to be doing in this course. Okay. So from that perspective, I have no issue just dealing with the real line because, and I discussed this in like the third to last video, doing everything we've done for higher dimensions is pretty easy. Even doing everything we're doing for in a very abstract setting, particularly the setting of probability, is pretty easy. Okay. Second, well, in practice, and when I say in practice, if you want to study things like Fourier series, the Fourier transform, if you want to solve PDEs, if you want to prove results about PDEs, You want to do other things in applied math, data science. The Riemann integral just kind of sucks. There's no other way to put it. It's pedagogically beautiful, and that's why we teach it in Calc 2 and undergraduate mathematics. But really, in doing research, the Riemann integral is just not good. And we just need a better integration process. And well, that better integration process is the Lebesgue integral. It's a generalization. Sorry, that was an S. Lebesgue. Whoops. Sorry about that. Hopefully there we go. Right. So we will develop what's called the Lebesgue integral, which practically speaking is a generalization of the Riemann integral that basically is as good as you could possibly want. It's an integration process developed in the early 20th century. And for the most part, pure and applied mathematicians are very happy with it. So there are some generalizations of it and some weirder integrals, but more or less, this is the integral that mathematicians use. And everything we do to kind of develop this practical solution will be applied to developing the Lebesgue integral. And along this lines, I should say that this function here, I mentioned this is often called Lebesgue measurable sets. And this is going to be called, I'll do it in a different color. This function m here is going to be called the Lebesgue measure. All of this was developed by this guy, Henry Lebesgue, in the early 20th century. Remarkably, this was developed in his PhD thesis. Sorry about that. Yeah, so Lebesgue measure. Yeah, so very remarkable that he did this in his PhD thesis. But anyway. All right, so yeah, hopefully that introduction was useful. I apologize if people don't think it was a good use of time, but I think it's always useful to explain why the hell we're doing something. What's the point? But anyway, okay, so yeah, I know Professor Bachanu did a little bit what I'm going to do now, but I still think it's to make sure we're all on the same page. I'm going to start from scratch. So my first task is to basically cook up this script m. Okay, that's we're gonna. Well, I guess we're really gonna almost at the same time kind of begin to cook up the script m and begin to define this function little m. So to start really cooking up what this collection of subsets of the real line script m is, we need the notion of a sigma algebra. That's the key definition to do that. So let's say I have x. Big X is a subset of the real line. Really, X could be any set, but for our purposes, X is a subset of the real line. So we have the following definition. And it might be a little unclear why this is a useful definition. I'll explain that as we go along. So a collection of subsets of big X. So, power set script P of X is just a collection of all subsets of X. So A is just not the collection of all subsets of X, but some collection of subsets of X. So we say script A is a sigma algebra if the following is true. And So I'll often say that this is a sigma algebra of X, or it's a sigma algebra of subsets of X, or if I don't need to, if the reference to X is not really necessary, I'll just say it's a sigma algebra. So we want three things to be true. The empty set is an A. And again, why we want these to be true, we'll talk about this in the next video. So we want the empty set to be an A. If we have an A in script A, then I want X take away A to be in script A. So this is the complement of A in X. And I'm just using this tilde because the book does. And I'm going to try to stick with the book's notation, but this is just ordinary complement. It's all the stuff in X that's not in A. Okay, and last but not least, we want unions to be preserved. If we have a countable collection of subsets AK in script A, then we want the union to also be in it. Okay, so, right. So as a sanity check, we have two very canonical, but nevertheless useful examples of sigma algebras, no matter what X, big X is. First, well, let's just take kind of the silly collection of subsets of X, just the empty set and big X itself. Okay, so there's only two elements in this collection of subsets, but nevertheless, this is an example. And the other example, well, it's just a power set, the collection of all subsets of X. Okay. Okay, so let me prove the following proposition. Okay, so right, so if you have a sigma algebra script A, and if I don't mention what X is, it basically means it doesn't matter what X is. There is just some big X lurking in the background. Okay, and if we have each AK in script A, then three things. One, well, countable intersections, or the countable intersection of the AKs is also an A. You might have been wondering, well, what's special about unions? Why not intersections? Why exclude them? We're not. These properties, maybe I shouldn't do, I don't know, I'll call this big A here, I guess. Yeah, so we do have intersections are preserved, countable intersections are preserved. B, finite intersections are also preserved. If big N is an integer, a positive integer, then both of these are in script A. Okay, and C, if I have, let's just say A1 and A2, Well, yeah, let me put it like this. So maybe I'm being a little redundant here, but just to make sure we're clear, if I have any two um, sets in my collection script A, then that means A1 take away A2 is also in script A. All right, and the proof, I'll just go through it. The proof is really not too hard, not all that much to it. So let's just write, basically use basic AMAT 299 set theory stuff. So I would definitely review 299 set theory if you are a little uncomfortable with that, because we're going to use that a lot. So I can, of course, write any intersection as the complement of a union. And if you have any doubts of anything I'm writing here, frankly, you really should be able to prove it yourself. Prove that the left-hand side is a subset of the right-hand side and vice versa. Okay. Well, so we know by 3 here that one of the properties of sigma algebras is that you can take countable unions and still stay in the sigma algebra. So this is still in script A, this countable union, but we also know that we can take complements and we're still in script A. So, right, so that means this here is in script A. And yeah, I think from now on, I'm going to write this as just using the superscript C here, because it's kind of a pain in the ass to have to write X twiddle. So yeah, so and like I said, whenever we deal with sigma algebras, there's always some there's some big X lurking in the background. Everything is a subset of some big X, which for this course is a subset of the real line. All right, so yeah, that proves A, and I'll probably go a little faster in in the future. But anyway, so B, basically we already in some sense went through the proof of B. Think about it. So we know that the empty set is an A. So let's do what we did, I guess, 20 minutes ago or so. I don't know exactly. So let's define, sorry, let's not define, redefine to be, we redefine AK to be the empty set if K is bigger than N. Then what do we have? We have that, I'm only going to do this for unions. Intersections are exactly the same. So obviously this union here is going to be this countable union, because after K equals N, we're just unioning with the empty set, which has no effect. Well, everything here, we're assuming, well, all the AKs are in script A. And if we redefine AK to be the empty set for K bigger than N, then for K bigger than N, still the AKs are in script A. So everything's in script A. And we know countable unions of stuff in script A, is in script A. So it's in script A. Yeah, I'll occasionally have silly typos. Feel free to send me an email or even make a comment like, hey, professor, you did something stupid here. It maybe not put it that way, but even if you say that, I probably will not take offense. Um, I probably shouldn't say it like that, but anyway. Okay. Right. So yeah, and like I said, finite intersections are similar. I won't write it down. If you have any doubt, absolutely do it. Int for intersections. Okay, and yeah, C is really not much. C is kind of similar in style, I guess. So A1 take away A2, you can fairly clearly write as, well, the complement of A2, I'll just maybe one more time write as X take away A2, intersect A1. I mean, yeah, if you have any doubt, again, prove this. Left-hand side is a subset of the right-hand side and vice versa, but it's still pretty clear. The right-hand side is stuff that's in A1, but not in A2. That's exactly what the left-hand side is. Well, right, so this is in script M. This is in script M. We know finite intersections are finite intersections of stuff. I did it again, sorry. Yeah, this is in script A. This is in script A. Finite intersections of stuff in script A is in script A. This is certainly a finite intersection. So this is in script A. Okay. And that ends the proof. So I'll use a square filled in rectangle to end the proof. Okay, I want to do one more thing before I finish off. And in the next video, we will put this to good use. So I need the following proposition, which will lead to an extremely useful definition. So let's say I have any collection of sigma algebras with, let's say there's a common big X lurking in the background. So I is just big I here is just some generic indexing set. This is just a generic collection of sigma algebras. So let's say this is a collection of sigma algebras of some big X. Just write that to make clear that big X is not changing. Then it turns out that the intersection of all of these is also a sigma algebra. Of X, right? Okay, yeah, and let me prove this. The proof is really pretty straightforward. I'll try to go a little quicker. Okay, so what do we need to do? We need to check all three of these properties, right? Yeah, so we need to check, yeah, we need to check all three of these. The empty set is an A, complements are preserved, and countable unions are preserved. Okay, right. So yeah, let's start off. Well, there's not much to this here. So for each alpha, Well, the empty set is in A alpha, so that means that the empty set, by definition of intersection, is in the intersection. Really, not much more to it than that. Okay, let's say A is in the intersection of all of these. Whoops, sorry about that. This is script. Yeah, so big non-script A is going to be something, an element, a collection of subsets of X. Big A without a script, without a cursive is going to be a subset of A, subset of X rather. Script A is going to be one of my sigma algebras. Okay. So let's say A is a subset of X that's in this intersection here. Right, so what does that mean? That means A is in each one of these. Each one of these is a sigma algebra. So that means X, take away A, complement of A and X is also in each one of these. And so it's in the intersection. Okay, so that's going to apply, right, by definition of intersections, really not much more to it than that. This is going to be in the following intersection. Okay, that proves 2. Yeah, I'll leave 3 as an exercise. I won't collect it, but maybe I'll just do it real quick. If you think it's a waste of time, feel free to skip it when you watch this video. Absolutely not offended if you do. Yeah, so let's say AK is in this intersection here. So it's in every one of these. Basically, it's the same proof idea. That means AK is in each A alpha for each alpha fixed. Put that in here. Well, for each alpha fixed, this is a sigma algebra. So that's going to imply that the intersection for each alpha fixed of these AKs, and maybe to be a little clearer, this over. Let's assume AK is in the intersection for each K, a natural number. Okay, so right, so AK for each natural number K is in the sigma algebra. Because of the sigma algebra, that means the intersection is in this sigma algebra. And because this is true for each alpha fixed, that means the intersection of these AKs, the countable intersection, is in the intersection of all of these. And that finishes the proof. Yeah, and maybe make it a little clearer. This is again like just what we just did. Excuse me. Here we're fixing an alpha. Um, yeah, we're fixing an alpha, and because this in red is true for every fixed alpha, that means it's in the intersection because it's in every single script A alpha. All right. Yeah, so a very easy proof. Yeah, so let me finish off with a very important definition. So let's say I have script F is a collection of subsets of X. Okay. It's just some collection of subsets of X. Okay, that's it. So really trivially, or really what we just proved, maybe it's not trivial. So there exists well, no, it actually is trivial, sorry. There trivially exists a sigma algebra of X containing script F. And in the next video, actually, script F will be all the open subsets of the real line. We'll also talk about script F being all open intervals of the real line. So really, we have a very concrete F in mind, but we'll do that. We'll put what I'm going to do to good use in the next video. Well, you should be able to figure out what the sigma algebra is. That's just a power set. Power set is a sigma algebra. It contains all subsets of X. So whatever script F is, it contains script F. Okay. So we know that if we take intersections of sigma algebras, we still have sigma algebras. So what we want to do is we want to define a sigma algebra as follows, which I'll call it script A. It's just the intersection of all sigma algebras So it's the intersection of all sigma algebras of X containing, it's down here, containing script F. So maybe make this a little bigger. I'll make the intersection a little bigger. Okay. So this is called, this is a very important definition. It's a sigma algebra generated by script F. And again, really what we have in mind is very practical script F, particularly, all open subsets of the real line or all intervals, closed intervals of the real line, something like that. Okay. Right. So I'll end this with a proposition. And the point here, it's basically, really, there's almost no, basically, it's almost already proved, this proposition. There's really not much to prove. So by definition, this script A that I just defined, let me move this back here. is the smallest sigma algebra of X containing script F. Okay, and what is the proof? And maybe if I'm not clear, I should, when I say script F is, all open sets or all open subsets of the real line, or all closed intervals of the real line, I implicitly mean that big X is the real line. For the most part, and we're going to have X is the real line. So, right. Particularly when it applies to this definition, sigma algebra generated by script F. Okay, the proof, well, yeah, like I said, there's really not much to the proof. Well, we know that this intersection is a sigma algebra. We just proved it. We know it contains F because each one of these contains F. Each one of these script A primes. So you take the intersection of all the script A primes that contains script F. So this is a sigma algebra of X. And I apologize if I'm being a little messy. Really should try to do a better job in the future. Anyway, so it's a sigma algebra of X containing script F. Finally, if we have, let's say, for lack of anything better to call it, script A tilde, if this is a sigma algebra of F, of X, containing script F, well, then script A tilde is a part of this collection here. Script A tilde is absolutely in what I am circling. And hence, script A is smaller because script A is the intersection of all the stuff I just circled, one of those things being script A tilde. So just absolutely trivially, that means that script A is smaller. So that's what we mean by script A is the smallest sigma algebra containing F. Any other sigma algebra of X containing F is potentially larger in the sense that it is a superset of script A. It could be equal, but at the very least, it's it's bigger or equal to. Yeah, and that proves it. Right. So in the next video, we will talk about the Borel sigma algebra. More precisely, script F will be exactly all open intervals for real numbers A and B, where A is less than B. So yeah, and if I get complaints that I'm being too slow, I will speed things up. But I always like to err on the side of caution when filling in details. All right, well, so long, take care. Yeah, we'll see where we get. I hope that we can finish up Lebesgue measure and talk about measurable functions and get to Lebesgue integration by the end of the semester. And I have the whole theory of Lebesgue integration online already on YouTube. So, all right, so long, take care, bye-bye.